All right, let's look at the last homework set. 49.4 has you integrate z to the 1/2, a particular branch of z to the 1/2, about contour c sub 2, and the branch of z to the 1/2 they're giving you is usual stuff for branch of a square root function, and they're requiring the angle to be between 0 and 2 pi. And the story here with c sub 2 is it's a contour that starts at -3, it remains in the lower half plane, and it ends at +3. So we've got a little problem here. This branch of the logarithm isn't defined when theta equals 0. That affects this right-hand endpoint here. At 3, the argument is 0. This branch of the square root function is not defined. So here's what we're going to do. And the wording of this one in the book is a bit clunky. We're going to take this branch of the logarithm, I tried to color code them, this one in black, replace it with this branch of the logarithm in blue, where here we're taking theta, usual square root stuff, except now we're taking the theta values to be between pi halves and 5 pi halves. So there's lots of overlap between this branch of the square root function and this branch of the square root function. They overlap from theta between pi halves and 2 pi. I think they'll overlap, excluding the endpoints. Well, that's perfect because the relevant theta values here are theta between pi and 2 pi. So we're getting agreement between this branch of the square root function and this branch of the square root function, not everywhere, but at all the points on c sub 2, except for that red endpoint at 3. Okay, so if the integrands are the same everywhere except at a single point, then the integrals are the same. So what we're going to do is evaluate this integral, show it takes on this value, by replacing the black branch of the square root function with the blue branch of the square root function and integrating it. Why you want to integrate the blue one? Because it's defined and continuous throughout contour c sub 2. That's the point of the exercise. So we'll make the replacement, and you need to do two things. You need to actually compute the integral about c sub 2 for this square root function, the blue branch of the square root function, and show it takes on this value. And then you need to say, well, the integral of the blue branch of the square root function is the same as the integral of the black branch of the square root function, because on contour c sub 2, these give the same value, except at one point. And that's why I colored that endpoint red. They differ at a single point. Changing the integrand by a single point doesn't change the value of an integral. That's the why in the why these are equal. So compute using the blue function with this range of angles, get that out, that'll give you the value of this, explain why those two integrals are the same, that gives you the value of the black branch of the square root function, and that was the question. Again, the book worded it kind of clunky. They started out talking about this branch, then they had you use it to, this branch, the one in blue. And then they said use that value to explain why the integral of this branch is this value. That's what you're doing, but the computation will be done with the blue one. And the answer to the question is an answer concerning the black branch. Okay. 53.2 says, integrate around c1 f of z. Show that integral is, well, they don't ask you to integrate, they ask you to show that the integral around c1 of f is equal to the integral around c2 of f, where c1 is, it's a little 2 by 2 square. We've gone over to x equals 1, and then up and up to y equals 1, and over and down, and so forth. And they want you to show the integrals are the same over those two contours for this particular function, z plus 2 over sine z divided by 2. I don't think there's any of us that can evaluate this integral. Notice you're not asked to evaluate the integral, you're asked to show these two contour integrals are the same. Okay. Well, the principle of deformation says if we've got a function that's analytic on and inside two contours, C1 and C2, and I think C2 was a circle of radius 2. If we've got functions analytic on and inside these two contours, on and between these two contours, C sub 1 and C sub 2, so outside of C sub 1 and inside of C sub 2, that disk with a little square cut out of it, do we have this function analytic there? If so, principle of deformation says those integrals are equal. Well, where is this function analytic? As long as you don't get 0 in the denominator, we're good with analytic, says the quotient rule. But you do get 0 in the denominator. You get it at 0. So this function is not analytic at 0. Yeah, 0's not on C1 or C2, and it's not between C1 and C2. It's actually inside C sub 1. Not a problem from the perspective of the principle of deformation. Yeah, there's some other points where this is 0 as well, because that's a periodic function. And they lie somewhere along the x-axis. I bet you need to explain this. They lie outside of C sub 2. So I need to know precisely what C sub 2 is. I think it's a circle of radius 2. But we'll get zeros here and outside of C sub 2. Not a problem. Principle of deformation will then say integral around C1 equals the integral around C2 for this integrand, for this function. The hint is, where is the function analytic? It's analytic on C1 and C2 and between C1 and C2. 57.1, part A, says, what's the integral over C of e to the negative z over z minus pi I over 2? You're integrating over, and I had a typo in the initial version of the homework, you're integrating about a square that runs from x equals 2, y equals 2, x equals negative 2, y equals negative 2 as drawn here. The typo in the original set of the homeworks had 1s and negative 1s here. It matters because we're going to apply Cauchy's integral formula, and it's only applicable under certain hypotheses. But we've got square, a contour, which is a square, both sides of, length 4. So they range from negative 2 to 2 along the x and y axis. Anyhow, there's what we get for the contour. It's positively oriented. Hey, Cauchy's integral formula says, I know how to evaluate those kinds of integrals. We've got a function. We call it f of z. If you look at Cauchy's integral formula, is that function analytic on and inside contour C? Man, that function's the exponential. Well, e to the negative z. That's analytic everywhere. Not a problem. And we had a z minus z sub 0. So I put a square around the z sub 0. That's a pi I over 2. See, where is pi I over 2? It's on the imaginary axis. It's purely imaginary. Pi over 2. What's that? 1.5 plus a little bit of change. That's actually inside this contour. Okay, so z sub 0 is inside the contour, and that's exactly the setting we needed for Cauchy's integral formula. So apply Cauchy's integral formula, you'll get the f of z function, the e to the negative z, evaluated at z sub 0, and there's a 2 pi I floating around somewhere in the mix. But this is totally Cauchy's integral formula. The first version, it was theorem 50.A. 57.1, part B. Similar type story, except now we're going to need the general Cauchy's integral formula. We've got a function, tangent z over 2. In the numerator, that'd be your f of z. Where's that analytic? Not everywhere. So we'll have to be a little bit careful with where that function is analytic. It's a function of a real variable. It's got some problems, right? Tangent of pi halves isn't defined. So that'll have implications for where that numerator is analytic. So it's not entirely as easy as the first one because this was an entire function and this isn't. So observe where the tangent z over 2 function is analytic. We're given that x sub 0 is between negative 2 and 2. Okay, that puts x sub 0, puts it inside this contour. We're using the same contour in this one as in the previous one. So x sub 0 is I don't know. They won't tell me anything, but it's real in between -2 and 2. It's somewhere along the x-axis between -2 and 2, strictly. Okay. That puts it inside the contour, and that was part of the story with the general Cauchy's integral formula as well. So comment where this function is analytic. Comment that x sub 0 is inside the contour. Use the general's Cauchy's integral formula. There's an exponent of 2. I made it red to call attention to it. There's an exponent of 2 in that denominator. Here, there is no exponent or an understood exponent of 1. So that's why you need to go to the general's Cauchy's integral formula. All right, you got this f of z function. I think we'll need the derivative of f of z in the general Cauchy's integral formula. It dealt with exponents greater than 1 in the denominator, and it dealt with derivatives of certain orders. So you'll need the derivative, the first derivative, of that tangent function, tangent z over 2, and evaluate that at x sub 0 and keep up with the details from the general Cauchy's integral formula. There's 2 pi I floating around in that one as well. And I think a 1, well, a 1 factorial. So, and finally, on the graduate problem, you're asked to show that taking c sub r to be a circle centered at 0 of radius capital R, you're asked to show the modulus of the integral about c sub r of the principal branch of the logarithm divided by z squared is less than or equal to that bound over there. My hint is use theorem 4.43.a. That's the one that tells you about bounds on integrals. And let's see, you know what the modulus of z is? Yeah, we're integrating over a circle of radius capital R, centered at the 0, centered at 0. So the modulus of z is just r. So I'll produce an r squared. What's up with the principal branch of the logarithm? Well, you've got yourself a definition of the principal branch of the logarithm. You know some information about z. You know its modulus is r. Its argument could be anything, but you know its modulus is r. And let's see, somewhere in that theorem 43.a, you become concerned with the length of c sub r. It's be a circle of radius r. So it was a 2 pi r out of that. So I expect to see a 2 pi r here from the length of that contour. I expect from the z squared to see an r squared in the denominator, and I ain't got either of those. Well, or I've got both of those. Yeah, I expected another r in this numerator and another r in that denominator. So those have been canceled. And I leave it to you to deal with the pi plus natural log of r. That'll come out of the principal branch of the logarithm stuff. So that's how you'll get the bound. They also ask you to show the integral approaches 0 as r approaches infinity, and L'Hopital's rule will take care of that. And that's complex variables 2020.